Good day and welcome to the experimental video for experiment 3, the liquid vapor equilibrium of a methanol methylene chloride system. So what do I mean by liquid vapor equilibrium? Liquid vapor equilibrium describes the distribution of a pure component or a mixture of components between the liquid and the vapor phases. So if you look at these figures that are obtained from the internet, on the left-hand side, I've got the vapor-liquid equilibrium for pure toluene. So it just gives, if you have the same amount of toluene and benzene, you can see that the distribution of molecules between the liquid and the vapor phase is not the same. So for similar amounts of the two, I have more benzene molecules in the vapor phase at a specific temperature. So that is liquid vapor equilibrium. So it's a physical state in which mechanical and thermal equilibrium has been reached with no net mass transfer occurring between the liquid and vapor phases. So what that basically just means is if I have a specific amount of toluene at a specific temperature, I will always have a certain amount of toluene in the liquid and a certain amount in the vapor. And those relative amounts will remain equal, so there's no net mass transfer occurring between these phases. Then the liquid vapor equilibrium for a mixture of components is different from that of a pure component. So if you look in the middle, that is the mixture of equal amounts of pure toluene and benzene, and it depends on the temperature, the pressure, and also the amounts of components in my mixture. And the two components that make up the mixture will distribute themselves unequally in both the vapor and the liquid phases. Why are we interested in studying the liquid vapor equilibrium of a mixture of two liquids? So liquid vapor equilibrium, or if you look it up on the internet, they quite often talk about vapor liquid equilibrium, and they summarize it as VLE, plays an important role in chemical engineering and the design of separation processes such as liquid-liquid extraction and distillation. Some examples include the separation of petroleum products in the petroleum industry, the purification of crude oil, the production of ethanol, etc., etc. So if you are interested in further reading, just do an internet search on vapor-liquid equilibrium or liquid-vapor equilibrium and distillation or extraction. What you can also do is to just search Fischer-Tropsch synthesis and liquid vapor equilibrium. So that is the well-known Sasol process that is used for the production of hydrocarbons. And you will find a lot of information that is industrially relevant. So how do I describe my liquid vapor equilibrium behavior of a mixture? So what we will do is we will summarize the equilibrium behavior by constructing a graph that shows how the boiling point and the vapor and liquid compositions of a mixture of two liquids depend on the composition. And this we're going to call a boiling point composition phase diagram. So this is a lot of words. I hope that by the end of this lecture you'll have a better idea on how to do this. So in this specific experiment, we're going to look at the boiling point composition phase diagram of a methanol methylene chloride system using the system's liquid vapor equilibrium. So I'm going to explain Raoult's law now. The partial vapor pressure of the components of a liquid mixture are lower than the vapor pressures of the pure components. What do I mean by that? So I'm going to refer you back. Now I've copied the figure without the reference to literature, so please go back to slides earlier if you want to visit a specific website. But if you just look on the left-hand side, this is the figure for toluene, and this is the mixture of toluene and benzene. So if you look at that sentence again, the partial vapor pressure of the components of a liquid mixture are lower than the vapor pressures of the pure components. So for toluene, which are the white molecules, I've got less molecules compared to the pure, less molecules in the vapor compared to that of the pure component. And this vapor pressure lowering is directly proportional to the concentration of a component in a mixture and independent of the nature of the component molecule. Okay. So it's directly dependent on the amount of toluene that I had here in my mixture. So if I had only 50% of toluene, I will have 50% of my toluene molecules in the vapor compared to that of pure toluene. So that mathematically is described by Raoult's law. So Raoult's law says the vapor pressure of component A above the mixture equals the mole fraction of component A times the vapor pressure of the pure component A. So PA naught refers to the vapor pressure here of the pure component, and then PA just refers to the vapor pressure of toluene in my mixture, and GA, that is the Greek letter X, so we pronounce it G. So the mole fraction is calculated by G, and that is the number of moles of component A divided by the sum of components A and B for a two-component mixture. So the sum number of moles of A divided by moles of A plus moles of B. Let us talk about the vapor pressure of a binary mixture of two miscible liquids. Miscible just means that it's able to mix completely. So the total vapor pressure equals the vapor pressure of A plus the vapor pressure of B, and that you know as Dalton's law. So if I substitute Raoult's law in it, I will get the total vapor pressure equals the mole fraction of A times the vapor pressure of A in the pure phase plus the mole fraction of B in my mixture times the vapor pressure of B in the pure phase. I can then rewrite this expression only in terms of the mole fraction of either A and B. So in this scenario, in equation 3.3, I wrote it in terms of the mole fraction of A, just to have one less variable in my equation. So what do I do with this? I can use this to plot vapor pressure composition curves. And this will be for a system that follows ideal behavior, so there's no intermolecular interaction between my two liquids. So first of all, what does this plot look like? I have my vapor pressure versus mole fraction. And on the left, I've got 0, and this refers to mole fraction of B equals 1, implying that my mole fraction of A is 0. And on the right-hand side, I've got my mole fraction of B is 0, so that means my mole fraction of A equals 1. So I can plot three different scenarios. I can look at the partial pressure of A in my mixture, I can look at the partial pressure of B in my mixture, and I can look at my total vapor pressure of my mixture. So if I look at my partial pressure of A initially, I do not have any A in my mixture, so I will start there without any A. My partial pressure of A will steadily increase along the red curve up to this point. So if I have a mole fraction, if I have only A in my mixture, this will give me the value of PA 0. Okay, so whatever the value is there. So that gives me the vapor pressure of pure A. Similarly for B, I'm going to start at the right-hand side of the curve. If I initially have none of B and I increase in my mixture the amount of B or the mole fraction of B, I will end up here with the vapor pressure of pure B. So that would be PB0. Okay. So that will give me the vapor pressure of pure B. Now if I go back to equation 3.3, I can then also plot the total vapor pressure and the dependence of the total vapor pressure on composition, and that's given by the blue curve. Okay, so mathematically, it is described by equation 3.3. And then if I plot it, it's the equation on the blue curve. So if you look at that equation, it is a straight line curve related to the mole fraction of A. You will do more of this when you come to your theory component in theme 4. Now, in real life, most of the time, we do have interaction between your two liquids. So there can be some intermolecular attractions, repulsions, or some types of interactions. And therefore, you do not have an ideal system as you have on the left-hand side. So more often, you will have the types of curves that we have on the right-hand side here. Okay, so you can see deviation from ideal behavior for your total vapor pressure and also for your partial pressures of A and B. So in this scenario, if you look, the dotted lines would be for ideal behavior and the solid lines will describe the real behavior. Next, I want to talk about the Gibbs phase rule that shows the extent to which various parameters can be varied independently while the number of phases in equilibrium is preserved. And in our application, it refers mostly to phase diagrams. So the variance F, or the number of degrees of freedom, that's another name for it, equals C minus B plus 2. So variance equals C. Now C is the number of components. So if you have two liquids in your mixture, that means you have two components. P is your number of phases. So in this experiment, you will have liquid and vapor. So that's two phases, okay, plus 2 then. Okay, so your variance can be calculated from that. Okay, variance is just the number of intensive variables, for example, temperature, pressure, or composition, that can be changed independently without disturbing the number of phases in equilibrium. You are going to do this in great detail when it comes to the theoretical part of the module. For now, I think it will be best if you just remember that the number of phases you are working with would be liquid and vapor. So you've got two phases. You've got a two-component system because you have a mixture of two species. And then from that, you can calculate your variables. I will explain this more in the next slide. So if we look at our specific system again, we can calculate the variance. The number of components are 2 minus P, that's the number of phases. So we've got liquid vapor, so that's also 2 plus 2. So if I calculated that, my variance is 2. Now, if you think about our system, we have three variables. We've got pressure, temperature, and composition. So that means I always need to fix one of them. I only have a variance of 2. So I must always fix one, and then I can look at the dependence of the other two upon one another. Okay. So if I fix my temperature, I can look at the dependence of pressure with composition. If you think about the previous discussion, this is exactly what we did for the vapor pressure composition curves. Or if I fix my pressure, so I worked a constant pressure, I can look at the dependence of composition on the temperature. Or if I fix my composition, I can look at the dependence of temperature on pressure and vice versa. So you always need to fix one variable and then you can look at the dependence of the remaining two. So at a constant temperature, I can look at the variation of pressure with mole fraction. Okay, so I can obtain pressure as a function of mole fraction, and that is the vapor pressure composition graphs, which we discussed a little bit earlier. Alternatively, I can keep my pressure constant, that's the second scenario, and I can look at the variation in temperature with mole fraction. In this case, it will be my boiling temperature, but I will discuss it more later on. So that will give me my temperature composition phase diagram, and this is what you're going to be interested in this experiment. Why? It will be easier for us to keep the pressure constant, so we will just work at atmospheric conditions. It will be far easier for us to keep the pressure constant and then have specific mole fractions and then look at the temperature dependence thereof. Okay, so you are going to read temperature values for known values of the mole fraction at a constant pressure. In this experiment, you are going to construct your own boiling point composition phase diagram. So I'm going to attempt to explain a boiling point composition phase diagram to you now and just explain to you how to read it and how to interpret it. So these diagrams are determined experimentally by distillation. You can follow the experimental details from the experimental video for this practical. Now, if I look at this phase diagram, you will see that the boundaries here will show the composition of the phases that are in equilibrium at various temperatures, or at a specific temperature and a constant pressure. So this whole diagram is constructed at a fixed or a constant pressure, typically 1 atmosphere, because that will be atmospheric conditions. Now, the first thing I want to show you, so you have a temperature versus mole fraction diagram. The first thing I want to show you is that TA and TB on this graph represent the boiling points of your components A and B. So if I look at this figure here, so this is TB, that would be the boiling point of component B right there. And on the other side of my diagram, I have the boiling point of component A. So why is that the case? If you look at your mole fraction again, on the left-hand side of my figure, I've got a mole fraction of 0 for component A. So that implies if my mole fraction for component A is 0, my mole fraction for component B is 1. So that means I only have component B, and therefore at this point here, I only have boiling point of component B. On the right-hand side of the graph, I've got mole fraction of B equals 0. So that implies that my mole fraction of A equals 1, and therefore I only have the boiling point of component A. So for your two components, you will do the same. So on the left and the right hand sides, you will have to draw or substitute the boiling points of the pure components. Then the next thing, the top curve in your diagram is a representation of the composition of the vapor if the mixture is in equilibrium at the corresponding boiling point. So in this case, the top curve will give me the vapor composition. Okay, and then similarly, the bottom curve will give me the liquid composition. So if you think about what you have in your experiment, you are going to collect the vapor. So the composition of vapor will be given by the top curve, and then the composition of your residue from your experiment, or the bottom curve, will be your liquid curve. So in short, that is a very simplistic explanation of how to interpret and how to read this. So you will read your temperature values or your boiling temperatures using your thermometer. You will have your boiling points of pure A and B on your intercepts, and then the top line gives you vapor composition, bottom line gives you liquid composition. Now, just to show you, if you've collected a sample, just want to explain to you how to read your graph then from that. So if you have a liquid with composition A1 on this graph, so you are now busy with your distillation, you've attained equilibrium, and the composition of your liquid is at A1. So if you read it off, remember bottom line is the liquid composition. So at that specific boiling point, okay, composition of the liquid is A1. What would be the composition of the vapor? You have to move horizontally along the line. So boiling temperature for the mixture will remain constant. So keep to a constant temperature and go towards the right until you meet the top line, and that will give you the composition of the vapor. So if I have a mixture and the liquid has composition A1, so this specific mole fraction, the composition of the vapor will be far towards the right. Composition of the vapor will be A2. Okay, so for this specific mixture. Okay, so that will be the composition of my liquid and that will be the composition of my vapor at a boiling temperature of TA. This is exactly what you are going to measure or do in the laboratory. Now, my vapor will have a composition that lies closer to the more volatile component. So why do I say TA is more volatile? Because TA has a lower boiling point. Okay, so lower boiling point, so that will be my more volatile component. Okay, so the component with the lower boiling point will be the more volatile. So the vapor is richer in the more volatile component of my mixture. Now there's another thing you can do, and that is separation of two liquids. And in this specific example, it was a bit easy. So if you again take a liquid with composition A1, and I'm going to heat it to the boiling point. So if I take A1, I heat it to the boiling point, and I collect the vapor. So I'm now collecting the vapor phase from the distillation, and I'm cooling down the vapor phase again. Okay, cooling down the vapor phase, and I collect the liquid that I obtain from the vapor phase. I take that liquid and I heat it again. I will have a liquid now with composition A2, okay, from the liquid. What will be the composition of my vapor in equilibrium with liquid A2? So I have to move there. You can see that I will obtain basically pure component A in the vapor phase. Okay, so if I take this, remember, my boiling point would be here. So I'm just going to say T2 for my boiling point. So if I take that at that boiling point, I will obtain in the vapor phase pure phase A. Okay. Sometimes you have to repeat this procedure 2 or 3 times to obtain separation or to obtain a pure phase for the other component. So that just shows you by successive heating and cooling that you can separate your two liquids. You will do more of that in the theory module as well. And this technique is called fractional distillation. So if you're interested now and you want to read further, you can maybe just do an internet search on those keywords. The boiling point composition phase diagrams that we looked at on the previous 2 slides were those of ideal systems. So we already spoke about that most solutions are non-ideal, and therefore we can have more complicated phase diagrams. So in this example, I just want to show you an example of a boiling point composition phase diagram for nitric acid and water, and this system has a maximum boiling point. Okay, so it just refers to that point there, maximum boiling point in the temperature composition curve, and this is due to intermolecular interactions between nitric acid and water, which reduces the vapor pressure to below the ideal value, and it stabilizes the liquid phase. Okay, so you don't have to worry too much about that for now. You will also deal with that when you get to the theory component. So once again, even though this curve has such a strange shape, the top line, or the purple curve in this instance, so here, the one I'm highlighting in yellow, will still give you the vapor composition. And then the curve that I'm going to highlight in green, the bottom curve, will still give you the liquid composition. So you will do exactly the same. You will perform a distillation, obtain boiling temperatures, and at a specific boiling point or boiling temperature, you will obtain the composition of your liquid and your vapor, and you will construct your phase diagram. Okay, so maximum boiling point. You can also have a scenario with a minimum boiling point. And on the right hand side, this is a curve showing a minimum boiling point there. This is for ethanol and water. So once again, bottom line shows you the composition of your liquid, and then the top line shows the composition of your vapor. Okay. So all of this due to intermolecular interactions. I hope you've observed on the previous slide that for both non-ideal boiling point composition phase diagrams, the vapor and the liquid lines have met at a certain point or a single point, and this point is called the azeotrope. So at this specific point, the liquid and the vapor will have the same composition, you can read off from your x-axis, and it will also happen at a specific boiling point. So that will be the temperature of your azeotrope. When the azeotropic composition has been reached, distillation cannot separate the two liquids because the condensate has the same composition as the liquid. So an example of that, for water ethanol, the boiling temperature 78 degrees Celsius and a water content of 4% biomass. So please look out for that. You will also be requested to determine the composition and the temperature of the azeotrope in your experiment. So now let's briefly talk about the experimental aspects or the experimental setup for this experiment. Your setup will include a distillation apparatus. Luckily for you, all of this will already be set up in the laboratory. A heating mantle, burettes for dispensing the solvents, a refractometer, and then polytops into which you will make your mixtures. Please note that it's very important that your thermometer should not reach your liquid. So the height of your thermometer there should be above the liquid. If you're unsure, please talk to your tutor. He or she will direct you and show you the correct way to place or position your thermometer. Then please read through the procedure in the practical guide and make sure to watch the experiment 2 experimental video. Unfortunately, the position of the thermometer in the experimental video is incorrect. It should not reach the liquid, so it should be above the liquid. Another thing is that you should please do all your calculations. These are set out in section 3.4.1 in your practical guide before you come to the laboratory. Then also keep in mind that your results will be improved by preparing your mixtures precisely. Use the same refractometer for all measurements. So even if you work between groups or collect samples between groups, always use the same refractometer. And then correct and precise measurements of the refractive index and the boiling point values are of utmost importance. Please work patiently, ensure that your mixtures reach equilibrium before you collect samples. Also work continuously and do not waste time. This is quite a long and tedious experiment and you only have 3 hours to complete the experimental work. Prepare well and split the work between group members. Make sure that you use the provided fill-in sheet to collect your data and double check with your demonstrator that you've collected all the data necessary to compile your report. Please watch the experimental video before coming to the lab and remember to complete the pre-practical test on ClickUp. I quickly want to show you what to expect from your results. In part 1, you will determine the relation between refractive index and composition. And essentially, the two graphs which I'm showing here is the mirror of one another. So these are exactly the same. So you will plot refractive index. You're going to make up different mixtures with different compositions and then measure the refractive index for each of these and then plot that against the mole fraction of methanol or the mole fraction of methylene chloride. That will give you almost like a calibration curve. So these you will then use to determine in part 2 the temperature composition diagram. So in part 2, you're going to make up your mixtures and you will read off your boiling temperature. So while you're busy doing your distillation experiment, you will read your boiling point for a specific mixture. You will collect your liquid sample and you will collect a vapor sample for that specific experiment. You will then use your refractive index data, that is from the plots there, to determine what your compositions are for your 2 samples. Okay. And you will continue that way for each of your mixtures. So as you can see here, it's quite a number of data points that you are going to collect. The one important thing that I want you to take note of is that your azeotrope in this specific experiment lies far towards the higher end for the mole fraction of dichloromethane. Okay, so it's not in the middle, it's not a 50-50 composition, it lies more towards dichloromethane. So that's your azeotropic composition. So you have a very small a small bubble almost, I can say, towards the right here. So please just take note of that. Don't worry when your curves look like that. This is exactly what you should expect. And then have a good time, come well prepared and enjoy the experiment. Thank you for watching.